Well, good afternoon by now. Good afternoon, everyone. Thank you for attending the session. I understand we confused you with the wrong title outside on the billboard. This is a tech talk. I'm not going to talk about politics. I'm not going to complain, and I'm not going to ask for anything. Instead, I have something to offer. And in order for you to understand what I have to offer, we will have to include in this 20 minutes a full course of 6 semesters on quantum physics, because without it, it's a bit difficult. So we're going to do that in the course of the next 20 minutes. I'm going to talk about a bridge to quantum computing, and before I talk about the bridge, you need to understand what quantum computing is so that you understand that we need a bridge and how that bridge might look like. So why is quantum computing so important, and why is it being mentioned in all presentations and so on? Well, the reason is that quantum computing promises a next generation of computing that's 1 million times, 10 million times, 100 million times faster than what we can do today. Now, that doesn't say much, because what's 100 million or whatever? The real question is, does the industry, does mankind indeed have a few problems that require that kind of compute power? And I would submit to you that these problems do exist. In fact, they exist everywhere. We just need to have a different look at them and train our eyes to the computational challenges that we face today. They come in all fields, and I don't have time for all fields, but they do come in all fields, not just in theoretical mathematics, where certain complexity theory problems cannot be solved without quantum computers, not just what you heard about, namely how quantum computing might actually break a big part of the existing encryption schemes today. It can indeed when it arrives. So the current encryption schemes that are in use by banks and other institutions, if they use a public-private key scheme, are probably toast when quantum computing arrives. And therefore we need to talk about that one too. How long does it take? But this is still not exciting. It gets more exciting if you go into materials design, and that's not the material design of Android. Materials design, that's the discipline where you design molecules and compounds and other materials according to specification. That can be started these days with computers, but of course the larger the molecules get, the more complex the problem gets. It becomes very quickly intraceable using normal computers and normal computer technology. That can be taken into drug design as well. These are not the drugs. These are the drugs of healthcare and medicine, into drug design as well, and it can do arguably lots of good for mankind. That kind of compute power can solve very simple problems, such as what is the proper dosage, and how is the proper dosage administered to a cancerous tumor in the human body so that it doesn't destroy any other tissue and the treatment doesn't become a big problem as it typically does today. So how to do that real time on an individual basis. It's got to be then real time, because the patient is then, while the patient is being treated, this gets recomputed all the time and adjusted and so on. So these are the numerous possibilities and opportunities. However, I would like to, we are in Germany today, and Germany is by and large a manufacturing country. Manufacturing is the discipline that can immediately profit from the use of any next generation compute technology, because believe it or not, and I had to learn this the hard way too, we not only have theoretical mathematical problems such as the traveling salesman problem, which is very difficult to solve if the number of cities that need to be visited is too high. It's not just the knapsack problem, which is intractable in terms of complexity as it grows with the number of items that you pack into your backpack. You need to look up these things if you're not familiar with that. Very simple mathematical challenges that become very hard to compute if the number of items involved is high. Not only that, but it turns out, and I'm going to give you a very simple example, that in any manufacturing process, in about 15 minutes, we can identify problems that can be critical, that can be crucial. There are relevant for the manufacturing process, and if they can be computed real time or near time, which is almost real time, then we have won something. Now, we start the 6-semester course on quantum mechanics, and obviously we are not going to go to a big detail, but there are 3 things that I need to mention, and 2 of them I have to explain to some extent. The first one on the left-hand side is the crucial one. That's the concept of superposition. So if anyone wants to summarize in just very few words why quantum computing is going to be so powerful, the answer is through superposition. Now, almost everything I say is true. There is a great degree of simplification in it, of course. But superposition is something that only quantum systems can do. It turns out, and there is no doubt, this is not just a theory that might be right or might be wrong or something. This is a proven theory, and it's not new. It has been worked out in the beginning of the 1900s. And a couple of Nobel Prizes went for the theory. It has been proven in many ways, so there's no doubt that there is quantum physics. We just don't see it in everyday life, but it does exist in very special circumstances. And quantum systems have a property that's very strange. Well, we can even call it bizarre. It's a bizarre property. Quantum systems are not in a particular state at any one time, but in a number of particular states. Now let's get that down to computing. In computing, normally we have the bit as the simplest, as the simple unit, and a bit can have a value of 1 or 0. In quantum computing, a quantum bit can also have the value of 1 and 0, but at the same time, simultaneously, at the same time. So a quantum system is at any one point in time in both of those states. And if you do computation, and if you don't have 1 bit, but for the argument's sake you have, say, just 64 bits, then that system, that computer, can be at any one point in time in all of the states 2 to the 64, which is quite a large number. And so if you are smart about it, then you can do the computation for all these possible states at the same time. So even if a quantum computer is slower, and very frequently quantum systems, we have toy quantum systems today, they work only in labs. The quantum systems, even if they are slower than a classical machine, through the fact that they are doing essentially all combinations at the same time, at the end of the day they win, and they win big time. The bigger they are, the better they win. Keep that in mind. Superposition, we're going to need it in a second. And then there is this other one that I'm just mentioning. There's a phenomenon called quantum tunneling. Quantum tunneling is bizarre too. And if we had tunneling in our real world, if I took this clicker and threw it at the wall, there would be a very substantial probability that it flies through the wall, and the other side somebody can catch it. In the classical world that we live in, this probability does exist. It's not 0, it is just very, very small, and therefore don't try. It needs very many attempts before it might or might not succeed. But that's an important thing, that quantum systems can get through barriers very easily. And the third one, I have no time for it. Quantum entanglement is a bizarre thing too, and look it up. The German word for it is Verschränkung. Look it up, it's a bizarre thing. I'm not going to need it today. Now, superposition, application of superposition right now. You can go into your favorite search engine right now and try this. You type in quantum computing will, and the autocomplete will tell you that it will never work, and also it will change the world. And now, of course, you know what superposition is. Obviously, the correct answer is a superposition of these two at the same time. Both of them are true. We just need to see how do we do the computation with it. First application of superposition, this was in JIST. Now, I'm going to classify quantum computing systems for you today, and in the middle of what you see is the quantum gate systems, or also called universal quantum computing. This is akin to what we have with normal computers today. There are gates for basic logical operations. They work in a quantum nature, and if you combine them in a clever way, you can do something useful with it. That's the holy grail. That's what we all want, and that's what we all do not have. Now, if you read the announcement of certain companies that they have it, yes, they have it on this scale. It works in a lab. It works at close to zero temperature. That's not our zero of everyday life. That's the absolute zero of physics, 273.15 degrees centigrade, very cold, colder than the universe. And it takes a lot of energy and effort to keep a system at that temperature. It also needs to be shielded electromagnetically in all other ways, because the slightest disturbance to a quantum system causes it to decompose. That's the word we use. It means it loses its quantum state. When it loses its quantum state, the superposition is gone. So there's a problem that all the advantages I was teasing will not work at that point in time. That's the holy grail. It doesn't really exist in any practical form, regardless what the marketing materials of certain companies say. Now, on your right-hand side, left-hand side, you have quantum annealing. That's a smaller, simpler, less capable version of this whole thing. And annealing is a method that helps you to find minima of something like energy minima in a very complex landscape for a complex cost function, energy function, or something like that, by using quantum mechanics. In particular, if a system is in a state like this one right here I'm pointing at, these systems have a difficulty to surmount the energy barrier, even though it is clear that there is another one that's even deeper lying. So obviously we would like to get there. There are ways to facilitate that, but quantum physics with the quantum tunneling helps you do that. That was my second thing that I mentioned, that this energy barrier, just like a wall in quantum, can be surmounted, and therefore you get to low-lying states, and these systems converge very fast. And therefore, if you can formulate your problem as a combinatorial optimization problem, this method, which is a subset of these, much smaller, it can only address combinatorial optimization problems. So the interesting question is, you can see here in the slide, I took away the word quantum. So if this works this fine, then I'm asking this question. I don't have the money, the double-digit millions to have a quantum computer. I cannot keep it for a long time at such a low temperature, because it costs a real amount of energy. It's expensive, and the shielding and everything. So I just take away the quantum of it, but everything I learned in quantum physics I'm going to apply as well as I can. The question is, do I still have an advantage? Good question. So I said it's only applicable to combinatorial optimization. This sounds like an enormous limitation. Like, I gave up the universal nature of quantum computing. I cannot tackle any problem in the world. I can only do combinatorial optimizations. So when your eyes are dry now and you stopped weeping, I tell you that these are the most interesting problems in the world, relevant for industrial production and optimization. And doing just this is a huge, huge step for mankind, industry, health, math, physics, medicine, and everything in all of these areas. Because if you look at any one of these problems, you do molecular design just with 50 atoms, you have 10 to the 48 combinations. But here's a nice one. You are in the financial industry, you have a portfolio of high-value liquid assets, and the markets are moving. You want to optimize that portfolio, the number of things just with with 500 stocks in it, or 10 to the 150 combinations, the universe has 10 to the 77 atoms, so that you can feel how big and complex this is. So, looks like a limitation. It isn't. It's a cool thing. Now, we go back to manufacturing. Oh, my time is getting short now, so I need to speed up at this point. Apologies. So, we look at the manufacturing situation. A chassis of a car is being pushed in, and the robotic arm needs to do the welding and the shielding. So what happens now that I have a number of points where I need to apply my welding, and the seams that need to be drawn, typically more than that, but let's just take this. 64 ones. So the question is for the robotic arm, in what sequence? Well, that is the traveling salesman problem, sequencing the things. And also then, there is this other question of, if I have a seam that I need to seal, do I do it from left to the right or right to the left? If you take all these possibilities into account, you will end up with 2 to the n minus 1 times n minus 1 factorial. That's the product of all numbers on t from 1 to n minus 1. Anyway, if you don't know what that is, not a problem. I'm telling you, if you have 64 points, the possibilities are 10 to the 106. Mind-boggling. Now, can I do, if I took away the word quantum, and I'm just applying the disciplines of quantum physics and the methodology, can I do something useful here or not? Well, the answer is, depending on what you call useful, because if you are expecting a speed up of 100 million, I can't give you that. Quantum computers someday might be able to give you that, but our technology can give you something that is, say, 8,000 times or 10,000 times faster than anything we have today. Now that's beautiful because 2 hours, which is needed for a kind of computation like this, are 7,200 seconds. You knock it down with the factor of 8,000, what you end up with a sub-second optimization. And if it's sub-second, then you are relevant for the production. That's near time. We can do that. And the way to do this, and now I'm with the bridge, the way to do is we have a technology that's, mind my words, not quantum. It's not in a quantum state. It's a digital technology, very particular, nothing like you've ever seen. It cannot do anything else. Microsoft Word doesn't run on this. But what it does, if you properly formulate a function, a complex function, it gives you the minima of this function. So for combinatorial optimizations, just fine. So we do a kind of superposition trickery inspired by quantum superposition. We do a kind of quantum tunneling trickery inspired by quantum tunneling, and we do mimic entanglement as well. With that, we have a situation where, a very strange situation, where in this manufacturing example, robot positioning of the welding robot, normal computers include, and the quantum computers cannot do. Quantum computers cannot do the very high numbers here because they are too small for that. Lab toy models. But our bridge technology for quantum computing can actually tackle that, which is why I painted it green. So we do have something that's called a digital annealer. It's not in a quantum state, but it uses everything we learned from quantum mechanics. It implements a kind of superposition mimicry, a kind of quantum tunneling mimicry, and a kind of entanglement mimicry. And with that, typically, it gives you a speed of typically 10,000 times, depending on what we are talking about. Now, I need to come to a finish. And I'm just going to tell you now that this is a new world. Not because it's so promising, it is. Not because it has the potential to solve the problems of mankind and sustainability and energy use, optimizations of batteries for cars. This is what we are using it for already in proof of concepts. That's cool. However, it can change the ecosystem in ways that many of you might be interested in because it redefines what programming means. These machines actually require an entirely different kind of programming that you know. And you know, when politicians are walking around, saying, everyone needs to learn to program. Yeah, like what? Java? Excuse me. So this is a totally new type of programming, because if it's a gate computer, then it's not really programming, it's an algorithmic development. And currently, for the universal quantum computers, the toy quantum computers, there are maybe 60 known algorithms, not more. And if it's not that, but the annealing type, which is more useful, then the job is not programming. The machine can only do what it can do. You cannot change that. What you can do, though, and you have to do, is take your problem, translate it in mathematical terms. That's called a mapping, a mathematical mapping, in a particular form, which is on the screen there. It's called quadratic unconstrained binary optimization. It needs to be in that particular form. Once it's in that particular form, your Python program doesn't do anything else but feed our machine, and that spits back the results in no time at all. So, to finish it, that's it in a nutshell. Currently, the bridge technology to quantum computing is more powerful than quantum computing itself, because the quantum computers do not exist. This exists, it's in the second generation, and it's working now. Now, here is Gartner's hype cycle. They have this hype cycle. Gartner says every technology needs to go through this cycle. So it's being invented, innovation, and it climbs up to the peak of inflated expectations, and then it comes through a valley of tears or trough of disillusionment, and only later does it become useful. Now, this doesn't work for quantum computing. You know now. You've been listening to the 6th semester course. You know that there is tunneling. So we're going to tunnel through this, this peak of inflated expectations and go immediately to industrial applications. And we've got the technology. If you have ideas, please talk to us. Thank you.
Thank you, Dr.
Thank you.